Hello, I'm Ryan with High Desert Math Tutor, and today I want to talk to you about antiderivatives. So at this point in calculus, you're starting to shift from differential calculus to integral calculus. And the first step in that transition is recognizing that we need to be able to undo taking a derivative, since typically anything we do in math, we want to be able to undo that operation. So antiderivatives are literally the opposite of a derivative. And knowing how to find antiderivatives is the first step of working on integration or integral calculus. So here, what we'll do is we'll begin by reviewing quickly what the power rule is. We'll look at a couple of examples with the power rule, and then we'll use antiderivatives to undo taking the derivative. So to begin, recall the power rule. So anytime you have a function where you have an x or a variable raised to some power, say n, if you want to take the derivative, you first bring the exponent down in front and multiply. Then you take x to the power n, but then you subtract 1 from whatever the exponent was. So that is just the typical plain old power rule that we're used to seeing. But let's look at that here in a concrete example. So here we have in Leibniz notation, we want to find the derivative of x to the power 5. So if we want to find the derivative of x to the power 5, we first bring the exponent down, 5. We multiply by x, and then we take whatever the exponent is, and we subtract 1 from the exponent. So we have our 5x to the power 4. Here we have one more example, but this example has a coefficient that's something different than 1. So as always, we bring down the exponent, then we're going to multiply 3x, but our exponent needs to have a 1 subtracted from it. And what we end up with is 21 times x to the power 6. So just a plain old power rule, taking a derivative, as we should be familiar with at this point. But now, a quick reminder before we jump into antiderivatives. As I mentioned in the beginning, antiderivatives are the opposite of taking a derivative. So antiderivatives undo the process of taking a derivative. So antiderivatives undo taking a derivative. So let's say we see here that when we take the derivative of this function, f prime of x, the derivative is 5x to the power 4. So let's start with this function and see if we can back up and undo taking the derivative. So we'll start with f prime of x, and we'll have 5x to the power 4. So to begin, if we want to undo taking the derivative of the left side of this equation, then we'll go back to just f of x. But for this right side of the equation, we have to be more strategic. Like let's actually use our knowledge of the power rule and strategically undo the process. So in the proper order, when we take a derivative, we first brought the exponent in front and multiplied. We secondly subtracted 1 from the exponent. Now we need to do those steps in reverse, and we need to do the opposite steps. So first, what we will do is add 1 to whatever exponent we have, and whatever that exponent is, that new exponent, instead of multiplying by it, we are going to divide by it. So in symbols, what we will do is we're going to take f of x, which is just, say, at this point, x to the power n. And then when we find the antiderivative, I'll use an uppercase F to represent the antiderivative. We will first add 1 to the exponent. Then whatever this new exponent is, we're going to divide by that number. So to see this formula in action here, we will first take our 5x to the power 4. We're going to add 1 to the exponent, plus 1. And here, I'll go ahead and do that in another color for you. So we will add 1. Then we will take this new exponent. We're going to divide by that same exponent, which will be 4 plus 1. So what we have here is 5x to the power 4 plus 1 is 5, divided by 4 plus 1 is 5. Now this 5 and this 5 undo each other, they cancel each other, and we just have x to the power 5 as a final answer. So to undo taking the derivative, you undo the derivative on the left side of the equation, we need to undo the derivative on the right side of the equation. But in order to undo the derivative, we have to do the opposite operations in reverse order. So the first thing we do is bring down this exponent, multiply. Afterward, we subtract 1 from the original exponent. Well, the opposite of that would be to first add 1 to the exponent. Thereafter, we divide by the new exponent. So let's see one more example right here of finding the antiderivative, and then we'll look at a couple of interesting details that we must consider that are kind of new to, something that it's kind of extending the first complication of calculus. So here, if our original function as a derivative is 21x to the power 6, to undo the derivative on the left side of the equation, we'll take the right side and first add 1 to the exponent, 6 plus 1. Then we will divide the whole thing by the new exponent, which is 6 plus 1. We end up with 21 times x to the power 7 divided by 7. 21 divided by 7 is 3, x to the power 7. So as you can see, we have successfully started with the derivative and worked backwards to the original function. But now we have an extra complication that it's time to bring up. So if you notice, both of these examples, for the sake of simplicity, had just a regular old x raised to some power, or x raised to some power, but we had a coefficient that was something other than 1. Well, what happens when we have something being added to the original function here when we take a derivative? So let's look at one last example. So this is going to be kind of the new progressive example that really highlights some of the complications to integral calculus. So first, we'll start with some arbitrary function. So I'm going to say f of x is, let's just say it's 6x to the 4th plus 3. So just some random function I make up. Let's take the derivative of this. So if we take the derivative of the left side of the equation, we get f prime of x. If we take the derivative of the right side of the equation, we're going to take the 4 down, multiply it by 6, we get 24. Then we subtract 1 from the exponent, 4 turns into a 3. And then the derivative of this constant number 3 is just 0. So that just goes away, and this is our derivative. Now, let's go ahead and jump into finding the antiderivative for this function. So, as before, if we want to find the antiderivative of this, the first thing we will do is find the antiderivative of f prime of x. We'll just undo the derivative. We get just regular f of x. Then here, we will first add 1 to the exponent. So we'll take 24x to the power 3 plus 1. Then after we add 1 to the exponent, we're going to divide by the new exponent, which is 3 plus 1. This leaves us with I'll just take it small steps. 24x to the power 4 divided by 4. Now we end up with 24 divided by 4, which is 6. X to the power 4. But notice, this is only a piece of what we originally started with, which was 6x to the power 4 plus 3. So this constant number went to 0. It became 0 when we were finding the derivative, but then when we undid taking the derivative, since we don't have any number here, we don't know if there was a constant number originally being added that we could back up and basically resurrect. So this is where a key difference between taking a derivative and taking an integral, where we kind of diverge the simplicity of the process. When you take a derivative, there's always a standard set of rules like power rule, product rule, quotient rule, chain rule. We use these rules whenever we take derivatives, and it's pretty normal for us to see constant numbers just become 0 when we're taking the derivative. But now we need to be able to back up our work and undo taking derivatives, but we can't come up with constant numbers that we don't know if they were there in the first place or not. So we see now that when we take derivatives and we lose information about constant numbers, if we want to have any chance of getting back to where we originally started, whenever we undo a derivative, we need to keep an open mind to if there was anything that could be missing that we just might not be aware of. To compensate for that fact, we have decided that any time you find an antiderivative, you're undoing a derivative, just in case there was some number that was a constant number that was originally there that has gone missing now, we should always add plus c to our antiderivatives to remind us that this is the primary portion of the function, the original function, but there's always a possibility that there could have been some constant number being added to the original derivative that has gone missing. Now, we won't get into differential equations too much today, but I just want to highlight to you that in the coming days, weeks, months, at some point, if you're continuing to study calculus, you will focus on something called differential equations. And a differential equation sounds impressive, but it's really simple. It's just an equation that has a derivative in it. So typically, if you start with an equation that has a derivative in it, and your goal is to undo the derivative, so you want to find the antiderivative, then we call this a differential equation. We find our antiderivative, but because we always want to add plus c when we are unaware if there was some original constant number being added, we call this a general solution to this differential equation. What that means is we have found an antiderivative, but because we're not sure if a constant number was originally being added, if we add plus c, you could put any number here. It could be infinitely many constant numbers like -5, +2, -356. Any of those numbers could be substituted into this part of the equation for c. And until we have additional information, often called an initial condition, we won't know what number should go here. So at this stage of calculus, when you find antiderivatives, the key is to remember that anytime you're finding an antiderivative, you want to add plus c just in case there was a constant number that was originally part of the function that turned into 0 when you took the derivative. When you do this, because this could be any number, just any number in general, we call this a general solution. And if you want to be very technical, any equation that has a derivative in it is called a differential equation. So this antiderivative, when you get rid of a derivative from an equation that has a derivative in it, you would say this is the general solution to this differential equation. Yeah, it's getting pretty wordy. I know it's getting a little bit complicated. It's a little bit beyond the scope of just the introduction to antiderivatives, but I've seen students that right off the bat get questions about finding general solutions to differential equations when realistically we should just be focusing on how do you undo taking a derivative. So we won't let those details bog us down too much. But one last point I really want to emphasize about the process for finding antiderivatives will arise if we talk about finding the antiderivative of a trig function. So as one last example, let's consider f of x being, say, sine x. Well, what is the derivative of sine x? The derivative of sine x is cosine x. But now let's say we want to go backwards, find the antiderivative of cosine x. At this stage, it's our job to not try to rely on a formula, but to use our knowledge of the cyclic nature of sine and cosine when you take derivatives. So there's always a cyclic pattern. We start with sine, take the derivative, it becomes cosine. We take the derivative of that, it becomes negative sine. And finally, we take one more derivative, we get negative cosine. And from that point on, it repeats. That pattern of taking derivatives of sines and cosines repeats. Well, with that forward motion of the pattern, we can also turn that around and just back up going through the derivatives. So we know that the derivative of sine becomes cosine. That pattern doesn't change. So if we are trying to find the antiderivative of a trigonometric function, we typically use our knowledge just to say, what do you take the derivative of to get cosine? Well, to get the derivative that becomes cosine, you have to take the derivative of sine. So at this point, to go backwards, to find the antiderivative, I'll go ahead and use blue. To find the antiderivative here, we say, well, we know that the derivative of sine is cosine, so that means the antiderivative of cosine must be sine. But don't forget, anytime you find an antiderivative, we can't assume that there were no constant numbers here being added or subtracted. So even here, we have to finish this by saying plus some constant number, just in case there was a constant number there that potentially went missing. So quick recap, and then we'll be good for today. So antiderivatives are doing the opposite of taking a derivative. We looked at the power rule, and we noticed that the initial steps for using the power rule were to take the exponent down and multiply. Then you subtract 1 from the exponent. But if we're going to undo that process, we need to do the opposite operations, but also in the opposite order. So the last thing we did here was subtract 1 from the exponent. So the first thing we do here is add 1 to the exponent. We multiplied by the exponent. Well, here we divide by the exponent. So we took a derivative of x to the power 5, found a derivative, and then we undid that derivative by finding the antiderivative. But after these initial examples where I just kind of showed you the general process, we moved on to the real process for finding antiderivatives, which is to do what we did here. We find the antiderivative, but the moment you find the antiderivative, in step 1, we need to say plus c in case there was a constant number in the original function that went missing when we took the derivative. So just for thoroughness, the appropriate final answer for this function would be x to the power 5 plus c. But in this instance, do you see a constant number being added to the original function? Oh, sorry. Right here. Do you see a constant number being added to the original function? No. So that means the number being added was 0, and that would just go away. And same thing here. We know that there was no constant number being added to this function when we took the derivative. But when we start with a derivative and we want to find the antiderivative, we can't assume that we knew there was no constant number here. So we have to add plus c to our final answer just in case, until we have more information. So a little bit wordy. I'm a little bit tired today, but I hope that was a good introduction to what antiderivatives are, and we'll see you next time.